It's a great pleasure to be here and to celebrate together with Jakob. It's also, I very much appreciate this opportunity to share some recent results on the polaron. So, first I want to talk about the mathematics of the polaron, but let me briefly introduce the physics background. And in the end, we will see that physical considerations are really a great source of motivations for the proofs I want to show today. So we have a negatively charged particle, and it travels through a polarizable medium. So this means it's maybe in a crystal with a very narrow lattice size, and this crystal consists of particles that have a positive component and a negative component. So initially, the crystals, the elements of the crystals, they are neutral, but due to the presence of the negatively charged electron, it will attract the positive part and repel the negative part of these components of the crystal. So we have this nice picture in mind that while traveling through the crystal, the electron polarizes its surrounding, and there is this idea that this electron is followed by a cloud of polarization, and this composite object of the electron and the cloud is what we refer to as a polaron. Now it's clear, this is unconfined space, so the electron will move in R3. Now it's a little bit more of a subtle question how we keep track of the polarization field. And the way this is done in the Fröhlich model is that at each point in space, let's call this point y, we're gonna measure the amount by which the positive charge is the positive part is displaced from the negative part. So this is just a real number, which I call phi of y, and this measures the amount of polarization at a given point in space. Now, I like this model for a multitude of reasons. The first reason is it's simple enough to allow for rigorous mathematical proofs, which as a mathematician I, of course, very much enjoy. However, there is a second property, and without the second property, the first property is worthless. Namely, it is complex enough to give rise to non-trivial phenomena. And one of these non-trivial phenomena is an effectively increased mass, which we have already heard about. So the idea is, due to the attached cloud of polarization, which attaches to the electron, the mass of the electron is effectively increased. And this effective mass, I will spend half of my talk to just define what the effective mass is in my framework, but let me immediately mention the main result I want to show today. And this is a conjecture which I refer to as the Landau-Pekar Spohn conjecture. So we have three names appearing here. And the way I understand it is, in this precise form, as I'm going to state it, this goes back to Spohn from 87. And it states that the effective mass, which I call MF, which depends on the coupling strength parameter alpha between your electron and polarizable medium, this diverges with the fourth power in the interaction strength. So you see, as soon as you start increasing the interactions between your medium and your electron, your effective mass drastically increases. And it's not just the fourth order divergence. Actually, there is a precise constant, which I refer to as ML subscript MLP, LP, of course, representing Landau and Pekar. And okay, then plus something that is subleading as alpha goes to infinity. And here, with this constant MLP, well, first of all, it's between 0 and infinity. This is an explicit constant, whatever explicit means. Constant, and this constant, the crucial point is this constant is predicted by the underlying Landau-Pekar theory. Now the thing is, the Landau-Pekar theory in this strong coupling model is nothing but the underlying semi-classical structure. And the nice thing for the Fröhlich polaron is that the strong coupling limit is equivalent to the semi-classical limit. So actually, for this specific model, the two of them coincide. And here we call the semi-classical theory, we call it Landau-Pekar theory. Okay. But it's basically a constant predicted by the semi-classics. So maybe it's a good point to mention at this talk that the methods we have used, Robert and I, to work on this conjecture, they have been inspired, a great deal of them have been inspired by beautiful methods in Bose gases that have been developed basically in this room by the people in this room. So really, a lot of the credit should go to all of you, because we really imported very robust and strong methods which have been developed to analyze the Bose gas, and we imported them to the Fröhlich polaron, and it turned out to be a very versatile tool. And maybe this is also a good point to mention, that I think these methods are actually very robust, and somehow the story should not end with the Bose gas. I think these methods we should try to import them also to different settings. I myself am nowadays working a little bit to implement them in a probabilistic and stochastic settings. So maybe this is a small announcement, but nowadays, so around springtime, I want to have a result on 542 theory, namely on tunneling in a 542 theory with a double well. So I unfortunately have nothing to say about Gibbs measures converging to, quantum measures converging to classical measures. So this will be just in the stochastic setting. The only quantum thing will be the methods. And those are beautiful methods, and it would be a shame to not try to import them to different settings. Okay, but let us come back to the polaron. Now, as it's tradition, a quantum model is described with two ingredients. So we need a Hilbert space, and we need a self-adjoint operator acting on the Hilbert space, which encodes all of your thermal and dynamical informations. Now, I'm talking to a very advanced audience, so it will be clear to all of you, but let me, for the sake of completeness, write down what the respective Hilbert space is in the respective self-adjoint operator. I think it's better to shift the blackboards. Let me start with the Hilbert space. This will simply be, well, we have a composite system, so we need to describe an electron, and we need to describe a polarization field. So the electron will take L2 of R3. That's no big surprise. This encodes the degrees of freedom of your electron. The second factor should encode the degrees of freedom of the polarization field. And as is well established, the right object to describe a quantum field is a Fock space, or it's at least a very good choice. So Fock space of L2 of R3. This is our Hilbert space. Now, I'm also going to define you. Okay, so we have a Fock space, so I need to talk about annihilation operators. All of you know them, but I'm still going to define them because there is a tiny twist. Okay, it's almost not worth mentioning, but then it is. Okay, so on an n+1 function, we annihilate one particle. So this is now only depends on n coordinates, and I define it. Well, basically, what you do is fix n coordinates, and you take the inner product with f. And then now comes the twist. Okay, of course, there's the square root n+1. And now I divide by alpha. This is my definition. So I'm baking the coupling constant into the definition of the annihilation operators. It's just to massage the formulas a little bit so they look nice. And then there's a second family of operators which is very iconic on Fock spaces. It's the second quantization of one-particle operators. With a one-particle operator, it acts on a psi n. How does it act? Well, okay. AX1 plus, and so on, AXN, and it acts on psi. Okay, great. Now, here you note, I find it more convenient to not bake the coupling strength into it. At some point, it's more convenient. And, okay, we will not need this in full generality. I actually only need this for two operators. Namely, I want to define the particle number operator, which is the second quantization of the identity operator on L2 of R3, okay, with a twist, so 1 over alpha squared. I'm counting the fraction of particles compared to alpha squared. And the second operator is the momentum operator of my quantum field. Momentum is usually measured in terms of the gradient, so this is the second quantization of 1 over I gradient. Okay. Now you see I'm a little bit sloppy. I'm not always indicating things that depend on alpha. I will rarely do this just to keep the notation clean. So annihilations operators with this are also, I think it's like, they are basically defined as strong coupling units is what I'm, no. Okay. Now with So what do we have? We have a Hilbert space, and we have two important families of operators, and now I can finally write down the Fröhlich Hamiltonian. And so I'm going to define the Fröhlich Hamiltonian. So this is one of the rare occasions where I actually indicate an alpha. And I define this as the direct integral over three-dimensional space of the following fiber operators. So this, for each three-dimensional P, there is a self-adjoint operator, H alpha of P, P. And now I need to tell you how the fiber operators look like. This is just, okay, direct integral. So this thing has three components. So total momentum P. So I forgot to mention this variable of the integration. This has the role of the total momentum of the system. So I subtract the field momentum and I square it. I add the particle number operator. And finally, I add an interaction term. So this is A of some function V plus the adjoint P. Okay. Now I need to tell you how the interaction V looks like. So V of Y is defined as pi minus 3/2. I think it's pi minus 3/2. Don't sue me. Y minus 2. Okay. Now you see this Y minus 2, this actually has a very natural interpretation, because remember we're talking about polarization. And this is exactly the electric field strength of a dipole interaction. Now if you look very closely, you see I don't have a direction here because I put the direction of the electric field under the carpet. It's an approximation, but yeah, in some sense, it would not be much more complicated to treat an electric field with a direction. It's just to simplify it a little bit. Okay. Now, yeah, please. Please, yes. I did. So I think this looks a little bit weird, and I'm going to comment on it because I defined it already in the Landau-Pekar picture. Yeah. So I'm going to comment. Yeah. So for me, this will be the usual Fröhlich Hamiltonian or a unitary equivalent version of it. So maybe we have different understandings, but yeah, maybe I will comment on it in a second. Okay. So let me maybe also talk about this object. It looks fancy, but it's the easiest thing you can do. Before I talk about what the direct integral is, let me make a comment. Namely, of course, you have the unitary equivalence of this tensor space to the space of function from R3 into the Fock space of L2 of R3. Okay, this will surprise no one. This unitary equivalence I can now use to define the fiber operator, or the direct integral. So what do I mean with this direct integral? Well, I mean that if this H alpha acts on a function psi, so remember psi, according to this unitary equivalence, is a function from R3 into the Fock space. So this, if I act with H alpha on this psi, this should again be a function of some three-dimensional input, and I simply define it as the pointwise action of the fiber operators, right? So at the P variable, I'm acting with H alpha of P on psi evaluated at P. So really, direct integral just means pointwise action. Okay, now let's talk a little bit about the interpretations of the three terms you see here. First of all, the first term is total momentum minus momentum of the field. Well, if you subtract from the total momentum the momentum of the field, the only thing that's left is the momentum of the electron. You square it. So the first term is just the kinetics of the electron. The second term is the particle number operator. This represents the internal degrees of freedom of the polarization field itself. So far, this is somehow, this describes only the electron, this describes only the polarization field. So naturally, the third term is an interaction. Now you should be skeptical about this because you see, these operators only act on Fock space. So you might ask, why do I refer to this as an interaction, right? And here comes the point. I'm defining this operator in the Landau-Pekar picture. Landau-Pekar picture, this is again just a fancy name to say that I'm measuring my polarization field in a coordinate frame that is co-moving with the electron, right? So if I want to measure my polarization field, I walk with the electron, and then I'm looking at the polarization field. And you see, if I would revert this Lilo-Pines transformation, if I would go into a stationary frame, what would happen in a stationary frame is that instead of the function v of y, what we would get is v of y, but now centered around x. And then in the stationary frame, you see, of course, okay, so this is the coordinate of the electron. Then you plug this into the annihilation or creation operators, and then you really see this actually acts non-trivially on both factors of your tensor product. So in the stationary frame, it's much more easier to see that this is an interaction. The reason why I prefer the Lilo-Pines picture is because here it's clear. Here it's clear that this operator commutes with the multiplication, with the total momentum operator. So here, really, the translation invariant is very manifest, which I prefer. Okay, so we have an operator, right? And actually, we have a family of operators. And now I can already tell you what the effective mass is. So we can define the effective mass of our polaron at some, okay, again, one of the rare occasions where I indicate an alpha dependence. And we define it as the limit of p going to 0. And what do you take? You take p squared, you divide by 2 times. I was too quick. I first want to define the energy, the momentum-dependent ground state energy. So this is momentum-dependent ground state energy, and it's exactly what you would think it is. It's the infimum of the spectrum. It's the infimum of the spectrum of your fiber operator. Right? And maybe for the sake of completeness, let me also define the total ground state energy, which is just the infimum over all p's of the momentum-dependent ground state energy, which is nothing but the infimum of the spectrum of the total Fröhlich Hamiltonian. Okay. So now we have momentum-dependent ground state energies, and this I use to define the effective mass, and it's just the fraction of p squared divided by the momentum-dependent ground state energy at p minus the same thing at 0. And it's actually known that the total ground state energy is obtained at 0 momentum. So you can also think of this as the total ground state energy. Okay, now a few comments. So this is not the only way how you could define the effective mass. I think one definition which could be considered more physical is if you say you somehow define the effective mass as somehow the response of the system to if you turn on an effective potential, and then you look at how the ground state energy changes, and you define the effective mass in terms of some response to an external potential. And Robert and Elliott have shown that this is actually equivalent to this spectral definition of the effective mass, which I prefer to work with because the spectral quantities are things I can actually control with variational principles. Second comment, maybe, we have to check that this is a sensible definition, and we do the most basic sanity check. If we would plug in for the energy momentum relation, the 1 over 3 particle. So if we would plug in for this E of p, just p squared divided by 2m, this quotient would always give m. So at least for a non-interacting particle, this definition of the effective mass gives you back the original mass. This is just a very weak sanity check, but it's good that it's at least consistent in this sense. And maybe let me also draw a little graph of what is happening here. So here I want to plot the ground state energy as a function of p, and it actually looks like this. So it's like a nice parabola shape, and then it gets flat. And now you see the thing that this effective mass tries to do is, now we just want to optimally fit in a true parabola into this picture. Okay, this was not very well drawn, but this function should be p squared divided by 2 times the effective mass at alpha, right? So in some sense, we just try to, we choose this effective mass such that we have an optimal approximation of the true ground state energy by a quadratic function, right? nothing more than this. So in some sense, we try to approximate the ground state energy function by the graph of a non-interacting particle with an increased mass. And so this is the effective mass, and now we have defined all of the objects that appear in the Landau-Pekar Spohn conjecture a few decades ago, which tells you, okay, this definition in terms of the spectral quantities, if you increase alpha, it actually diverges with the fourth power and with an explicit prefactor. Now I can tell you about a third reason why I think this is a very nice problem, because it actually has attracted the attention of different groups of mathematicians. So I myself, I work in the functional analytic universe, so I like operator inequalities, I like variational principles. However, this has also attracted, especially historically, also the functional integration community. So very famously, you can use the Feynman-Katz formula to give to express all of the quantities, these momentum-dependent ground state energies, in terms of functional integrals. And actually, for the large alpha asymptotics of the total ground state energy, this goes back to Donska and Varadhan multiple decades ago, who used this as a first, who used the very young theory of large deviations, or this as a first application of the theory of large deviations to actually get the asymptotics of this ground state energy. And I think it's nice. Okay, so there are multiple communities that work on the same problem. That's, yeah, I think it's a beautiful thing. Of course, the communication is, it's hard. Talking to people who do different stuff, that's very challenging. Okay. Now, I want to use this opportunity to give, I want to give you a hand-selected list of results on the effective mass. Okay. So my very offensive list starts with Elliot and Robert. It's offensive because it's very short. So in 2020, it has been shown that the effective mass actually diverges. So you see, really you would like to show that it diverges with the fourth power of alpha. But at this point, it was not even known that this would go to infinity. And if you read their proof, you see that this is a highly non-trivial statement they're proving. This is a proper theorem, and yeah, you see, it's a little bit tricky to prove anything for the effective mass. And there are two reasons for this. Namely, the first of all is, usually we want to work with variational methods, so we have upper bounds and lower bounds. But the thing is, it doesn't matter if you want to prove an upper bound on the effective mass or a lower bound. Since this is an increment of energies, you always have to prove both directions, right? If I want to have an upper bound on the effective mass, I need to prove probably a lower bound on this and an upper bound on this. Okay, so you always have both directions. But this is actually the more harmless reason. The much more severe problem is that you take the limit of p going to 0, and you want to show that this goes to 0 with p squared. So you have to have a very precise control on your energy increment of the magnitude p squared. And this is very hard to get. For example, semi-classical methods, they will always tell you, okay, this alpha-dependent energy, we can compute it as something constant plus something that depends on alpha, so maybe alpha minus 2. But the thing is, if you let p go to 0 faster than alpha goes to infinity, alpha minus 2 is very bad compared to p squared. So you see these things, they are always a little bit tricky. Now, afterwards, there was a huge surge of results, and there is there are multiple papers now. So this was functional analytic methods. Now we have a bunch of papers from the universe of functional integration. And the first one I want to mention is Betz and Polzer, let's say 23. And they improved this result by giving a rate. So they actually show that this is greater equal a constant times alpha to the power 2 over 5. And I think one of the most interesting things is that they used by functional integration some renewal processes. So they introduced some clever processes to get to this divergence. Now, if I'm correct, I think if you would dive into your paper, Robert, we would also get some rate, right? But it's probably not 2 over 5, or at least it's not written. Okay, so this was some improvement, but mainly it introduced a new method to talk about this problem. And we see also that afterwards there was a paper by Selke, and then there was a huge jump in the precision. So this was published in 24, and this shows almost immediately, this shows the almost optimal divergence. So they show that it grows with alpha to the power 4, but then there was some nasty log to the power 6. There's of course no physical interpretation at all. It's due to the methods. And afterwards, and this was basically, I mean, it's all roughly around the same time, there is a work by Masaes, Mukherjee, Selke again, and then Varadan from Donska and Varadan. And this is, I think, it's an archive version from 23. And it is shown that the effective mass actually diverges with the 4th power. So this is almost the ideal lower bound. The only thing that they could not get quite right is the right predicted constant. Okay. So now I told you I want to talk about effective mass. Now there is one result which does not really fit this list, but I still want to give it. So this is Polzer from Betz and Polzer, and it's, let's say, 23, where they showed that if you map some non-negative number t to E alpha, evaluated, let's say you plug in the first component square root of t and then 0, 0, small comment, E alpha is rotational invariant. So when I write this, what I really mean is you plug in any vector that has length square root t. Just for the sake of community, I put it in the first component, but okay. And the statement is this is concave. So this is really a statement that has nothing to do with the strong coupling limit or anything. This is more like, it tells you something about the nature of this function. And this was very lucky for Robert and myself because we could use this as an input. So we had a work published in 24, and there we showed, okay, the effective mass as a function of the interaction strength is bounded from above now by alpha to the power 4, and we immediately got the constant right. So this is the asymptotically sharp predicted constant plus something that is small compared to alpha to the power 4. So you see all of this was lower bound. So now we proved the matching upper bound, and we use this input that has originally been developed in the realm of functional integration. So we needed this concavity property, and the reason is exactly what I've said before. So the problem with the effective mass is that you need to control it on a magnitude of p squared. So in some sense, all we could really do was semi-classical results, which are good results in alpha, but not good results in p. And the thing is, this concavity exactly allows you to bridge this gap. Okay, so this is the literature overview from me, and the result I want to talk today is, okay, so at this point you see the only thing that is left to prove is the lower bound now with the correct constant. And this is the paper I want to talk today. So this was put on the archive in 24. And this tells you that the effective mass as a function of alpha is actually bounded from below by something that scales with alpha to the power 4 and exactly the right constant plus something that is small. And this is the result I want to give you a little bit of an idea. Okay, so maybe as a comment, it's quite surprising that this method does not at all work for the upper bound, and this method really lacks to prove the lower bound. And the reason why this doesn't give the lower bound is because the concavity only gives you one direction. Yeah. So really, in some sense, both of the results are needed. None of them is redundant. Okay, but so I want to talk about this today because, okay, first of all, it's the new result, and the second reason is that it's actually, so I think here there is a very clear physical idea which I want to show to you in the remaining time. Okay, so let me give a proof sketch. Okay, so we are done. once we find the elements psi labeled by the momentum variable in the Fock space, such that, first of all, this should be normed. Psi of p should have norm 1. But the crucial point is, if I look at the energy of this psi p, so I take psi p, I compute the energy at the p fiber operator, then what we want to show, so this is the difficult thing, I want to show that this is smaller equal the ground state energy evaluated at 0 plus something that is consistent with the Landau-Pekar conjecture, namely p square divided by 2 times MLP times alpha to the power 4, right? So this is exactly the green parabola I've drawn before. And then plus something that is small compared to p squared divided by alpha to the power 4. In this paper, I actually show that you can take this limit jointly. So in the joint limit of alpha going to infinity and p going to 0, technically speaking, you would only need the limit p first and then the limit alpha. But okay, so I get this in the strong sense of the joint limit. And why is this enough? Well, I told you I work with variational methods. So trivially, this is an upper bound on E alpha of p. So let me just emphasize this is trivial. And this is the non-trivial inequality. And now if you just juggle the terms around, you subtract E alpha of 0, you put it on the other side, you massage this term, you see immediately this inequality is equivalent to the lower bound in the Landau-Pekar conjecture. So once we have proven this inequality, we immediately get this result. And you see, okay, in principle, you need to plug in a clever choice of C of P. But now I want to convince you that this is actually a very subtle task. And the problem is that, first of all, the problem is you need, if P gets small, you need to be very close to the total ground state energy. But the total ground state energy is not an amenable object. I mean, E alpha of 0, this is nothing we have good control. I mean, there is no explicit formula for this. So in some sense, we have to be very close to this not easily trackable object. And okay, so let me first discuss the most trivial case, p equals 0. I mean, it's ridiculously trivial, but here we just take psi 0 as the ground state of the 0 fiber. Okay, perfect. If you take this, you have 1. I mean, nothing happens because if you plug in here p of 0 for the 0 Hamiltonian, you get exactly alpha of 0. You would have done. Now, the thing is, if we want to go to non-zero p's, we have to modify the ground state. So the task is we have to modify psi 0 and modify it to some function psi of p. And I talk about modifications because you see, in energy, you still need to be very close to the ground state energy, which also means that this psi of p needs to be in some sense close to the original ground state, up to some modifications. Now, there is one immediate guess anybody who sees this problem should try first. So let me call this the first attempt. Well, the first attempt is really trivial. You take psi of p, I simply define it as the total ground state, right? So my modification is that I modify nothing. This is, of course, the first thing one wants to try. And we can plug this function in and have a look how good this is. So I take the 0 fiber ground state, I evaluate it at the p-dependent fiber Hamiltonian. And you can do the exact computation, and this is just the total ground state energy, which is great, plus p squared. Okay. So there is one thing I like about this upper bound, and there's one thing I hate about this upper bound. What is great, there is a p square. And p square is good. We want to have E alpha of 0 plus something that depends on p square. However, there is a reason why this is a really bad one, because there's actually no alpha scaling. So the bound I want to have in the end should decay with the 4th power in alpha. This has no decay at all. So really, this is a terrible upper bound, or to put it equivalently, so this trial state is equivalent to the statement that the effective mass is greater equal 1/2, which is just the mass of the electron. So by plugging in this trial state, all you have shown is that the effective mass increases. Okay, I mean, it's an interesting statement, but it's very far from what we want to show. Then we want to show that it actually goes to infinity with a very fast rate. So let us have a look what went horribly wrong here. So what is the problem with plugging in psi0? Or in other words, where does this p square come from, which has no alpha scaling, right? The problem here is there's no divided by alpha to the power 4. And you can immediately see from the definition of the operator, yeah, there we have it. If you look at the definition of the p-dependent operator, there is one place where an p without an alpha appears. We have found the problem. Because if you plug in the psi0, you exactly get this p square. And this p square spoils you everything. I mean, since there is no alpha scaling in this p, as soon as you see this p, you have lost the game. And now you also see this p also appears in a square. So really, the only way to get rid of this p is if you have a cancellation between this and the momentum of the field. Right? So these two things, they need to cancel each other to get rid of this p, which doesn't have an alpha scaling. So now we can formulate a goal. Formulate the goal. Find cancellations between the total momentum p, which is just a given three-dimensional number, and the momentum operator of the field. And I want to discuss this on two levels. I first want to give my pedestrian physics view on this. What needs to happen in the physical picture? Well, let me have a hallucination about what I imagine would happen for a polaron, right? So I imagine that an electron, let's say it travels through unconfined space, and then it enters the polar crystal, right? And this electron has momentum, and it enters this crystal, it starts to interact with the polarizable medium, and by interacting with this medium, it will transfer its momentum in its environment. And so this means, this electron comes with momentum p, it enters the crystal, it transfers its momentum into the medium, and by this transfer momentum, it will get slowed down. And this process of it being slowed down is exactly what we interpret as an effectively increased mass. So you see, this cancellation between this total momentum and the momentum operator of the field, it can really be seen as this physical process of slowing down, transferring momentum, and therefore having an increased effective mass. So on the physics level, let's say, we want to transfer the total momentum P into only the field degrees of freedom. And the picture you should always have in mind is that the electron is somehow a very light object, highly oscillating, and the field degrees of freedom, they are like the massive slow degrees. And now if you think about the formula for the energy, it's energetically ideal to transfer your momentum into the heavy degrees of freedom. What this system strives for is to put all the momentum only in the field degrees of freedom. Okay, so this is just some intuition. In principle, you can ignore this slide, and let me just tell you what the mathematical idea is to implement this transfer of momentum. So let's talk about the mathematical implementation. Yeah, I was very slow. Okay. Okay, the mathematical implementation, let's think about a single particle in R3. How do you put momentum into this particle? Well, you apply the boost operator. You apply e to the power I x p, right? So you take this multiplication operator by a phase, and this is how you give momentum to a three-dimensional particle. And we do exactly the same. So what we do is we use a generator E. This is a family of self-adjoint operators, so three self-adjoint operators of boost, a generator of a boost. When I say a generator of a boost, I mean that if you conjugate EIPB with the field momentum, you get PF plus P. Here I'm lying a bit because this is not possible as an identity, but for all intents and purposes, this is. Yeah, it only holds an approximate sense, but in a very strong approximate sense. Okay, and then what you do is you simply define psi of P as this boost operator applied to psi 0. And what you see is that, right, so this is the thing we want to get rid of, but if you now apply the boost operator, you shift this to PF plus P, so you see exactly this, these two P's cancel each other, and you have got rid of the annoying P square, which has no alpha 4 scaling. Now, of course, you still have the other two terms. You have the internal degrees of freedom of the polarization field, and you have the interaction term. And now if you look at the expectation value, you still get something P-dependent. And now the name of the game is to find a good boost operator such that these terms give you the desired P squared divided by alpha 4 scaling. And I just want to finish with the sentiment that this is a very subtle task. For example, if you just plug in the center of mass boost, you actually get something that only scales. So for the center of mass boost, you only get absolute value P divided by alpha squared. So this actually fails in two regards. It doesn't have the right P scaling, it doesn't have the right alpha scaling. And really the subtle task is to find the right way to boost your system. And the way I do it in this paper is I use the semi-classical correspondence principle. So I map this unitary flow to a Hamiltonian flow, then I optimize within the Hamiltonian flow and use the semi-classical principle to pull this back to a quantum object. And yeah, maybe my last words. In this research on polarons, or in general on attractive unconfined systems, the first thing you want to try is the center of mass, but what Robert and I have figured out, a way better statistical quantity is to use the median instead of the mean value of your configuration. So we really learn from high school statistics here. Okay, thank you.